Oh, my book. Okay, physical science time. Physical science time. Today we are continuing our discussion about what in our book is chapter 17, which is the atom. We're going to go a little bit more about how to calculate the number of protons, neutrons, and electrons in a given isotope, and we're going to talk about the periodic table itself and valence electrons. Okay, so we're going to call this Atoms Part 2. Atoms Part 2. Part 1 having been yesterday. Some additional rules for finding the number of protons, neutrons, and electrons in a substance. First of all, let's talk about this. If I were to say the phrase subatomic particles, what does that mean? What does subatomic probably mean? We talked about what atom itself means yesterday. What's subatomic probably mean, Gabe?
Probably
Smaller than an atom. So in this case, from what we talked about yesterday, what are some of the subatomic particles? You could probably list some of them. Will? Protons, neutrons, and electrons. At least. There are more, but those are the ones that we learned yesterday. These are called subatomic particles because they're smaller than an atom. They make up an atom. Yes?
Can I see?
Sure. Subatomic particles make up the atom. They're sub meaning underneath. They're smaller than an atom. But there are more than that, and we have one type of subatomic particles are quarks. The word quarks, Q-U-A-R-K, is a quark. And those are even smaller subatomic particles. And the quarks make up just the protons and neutrons. Made of quarks. Electrons are their own little guy. Electrons, remember, they're very, 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 very small. Something like, and I don't remember the exact numbers, but I think it's something like if the nucleus of, let's say, a helium atom, a proton and a neutron, a helium-2 atom, sorry, 2 protons and 2 neutrons, a helium-4 atom, was a basketball. Okay, if that nucleus is the size of a basketball, and you had it in the middle of the football field, an electron would be about the size of a pea, and it would be on the very edge of the football field. So most of an atom is what, then? Nothing. Yeah, a vacuum. It's nothing. There's nothing there. Most of it is completely empty space. All the atoms that make up everything, even when you feel something that feels solid like this music stand, most of the atoms that make this up are empty space, and between the atoms is mostly empty space. And we're not going to get into how exactly that works, but you need to be aware that atoms are mostly empty space, and that the nucleus, even though it's where most of the mass, 99.999997% of the mass is in the nucleus, even though that's where all the mass is, that's not the whole volume of the atom. An atom is not like a Nerf ball that is just a kind of a solid thing the whole way through. It's mostly empty space. Anyway, so there are 6 kinds of quarks. Let's tell them right now. Up, down, top, bottom, strange, Q-U-A-R-K, strange, and charm. These are the 6 kinds of quarks. All what we consider normal matter is made up of these 2. And quarks are, they have to do with quantum mechanics. They're kind of spooky. Their properties are not, I would say they're well understood, but they're not really very easy to convey. Whereas things like protons and neutrons and electrons we can kind of just think of as their own object. Quarks are kind of messy little energy balls that are just excitations in the Higgs boson field, which really, that's a lot of stuff that we don't need to talk about. What we do need to know is that these things have a charge and a mass themselves. They have a charge and a mass. They have a charge and a mass. For an up quark, the charge is plus 2/3. And its mass is, it doesn't really matter. Something interesting about quarks is that even though a proton is made up of 3 quarks, it's always made up of 3 quarks. Even though it's made up of 3 quarks, those 3 quarks do not add up to the mass of the proton. On that scale, most of the mass actually is the energy that holds the quarks together, which once again, what energy would that be? What force would that be? Even that holds the quarks together to make a proton, probably. It's not gravity. That's right. It's the strong nuclear force. So it's still the strong nuclear force. But they also, in addition to a charge and a mass, they also have what we call a color. I'm going to put this in quotes because it's not color like, I'm not wearing anything colored. It's not colored like the green marker has the color green. We call this quantum color is a whole different thing, and it has to do with how these quarks can fit together. Don't worry about that. Don't worry super a lot about the mass. Those are just kind of interesting things that if you, like Gabe, are interested in quantum mechanics, you should be aware that those exist. But we're mostly going to focus on the charge, okay? So let's call an up quark, let's use red for up. That's not orange, that's red for up, and blue for down. And the down quark has a charge of negative 1/3. Why these weird fraction charges? Well, you'll see in a second. Like I said, all protons and neutrons are made up of 3 quarks. The subatomic particles that make up those subatomic particles are quarks, and they are always made up of 3 of them because of this property of color. So if I had, oops, I need to use red. If I had in my subatomic particle here this 1 up quark and 2 down quarks, which are held together, by the way, by what? The strong nuclear force. They're held together by the strong nuclear force. And this is going to form one of what 2 things? It's going to be either a what or a what, I already said. Yeah, it's going to be either a proton or a neutron. And how do we tell? Well, let's add up the little charges. What is 2/3 minus 1/3 minus 1/3, right? This is positive 2/3. What does that add up to? 0. This has no charge. So what subatomic particle is this? This is a neutron. Very good. Let's do the other one. So what other combination could we have?
We have 2 up quarks and 1 down quark.
2 up quarks and 1 down quark. Held together again by the strong nuclear force. Nothing else is different, just the arrangement of them. So now we have positive 2/3 plus 2/3 minus 1/3. Well, now what? What do those add up to? What's 2/3 plus 2/3? 4/3. What's that minus 1/3? 3/3, which adds up to 1. So what is this? A proton. So a proton is made of 2 ups and 1 down quark, and a neutron is made of 2 downs and 1 up quark. And these other ones, spooky. No one really knows, but normal matter is not made up of these things. This is only in very rare circumstances that we ever observe those, but they have been observed, and so they do exist. Normal matter is up and down quarks. Probably all the matter in this room, or all the matter you've ever experienced in your life, is made up of these 2 things and electrons. That's just the normal matter. We know that these exist because we've seen them in high energy collisions, like in the Large Hadron Collider that your book talks about, when they just take atoms and just moosh them together. It's like, the common analogy is that if you're a caveman and you want to know how marker works, you break the marker with a rock and you find out what's inside of there. I mean, there's better ways for modern human beings to figure out how things work. But as far as quantum mechanics, we're still on the level of the only way we know how to tell what's inside of these things is to just smash them together until they break and then see what comes out.
How do scientists like Crazy see? How do they even see?
Yeah, how can they see these things? Is that what you're asking? So they have this, and there's a picture in your book of the Large Hadron Collider, which is a gigantic circle, and they get a tiny particle or a group of particles. It's usually a little puff of gas, but it's a group of particles. They get that going with magnets up to almost the speed of light. They crash it into another group of particles going almost the speed of light, and then at the exact place where they crash, they have these detectors, electrical detectors, pressure sensors, all these kinds of things that are very sensitive instruments, and they can tell what comes out based on what things hit those sensors. And so someone's like, oh wow, that's like a quark, but it has a really strange mass, so we'll call that a strange quark. I don't actually know if that's where the name came from. Yes?
So in 2012, did scientists insert accelerate a particle so fast that it caught up to itself and interacted with itself?
I have no idea. That sounds cool though, Gabe. That is really cool. Let's we don't. That's very interesting, Gabe. I would love to hear more about that, but we don't really have time, especially because I don't really know about that, so I don't want to talk about it right now. But thank you for the. Let's look at page 510 together. I'm going to put it on the video for those of you at home who don't have your, or those of you watching in the future who don't have your book with you, you can probably read that if you pause the video. We're talking about different atomic models now. So this is the way it works now. We know that this is what's inside of these nuclear particles, and there's also electrons. And we talked about how electrons were yesterday. But from the very first time that people ever knew about atoms, remember the word atomos. The word atomos is from the Greek, meaning without being able to be cut. And this idea came from a philosopher named Democritus, who he did not have any evidence for this. He didn't like see an atom. I mean, I guess in some sense we all see atoms all the time, but he didn't like observe an atom and think, I'm going to name that atom. He was probably drunk one day because there was nothing better to do back then. So he was probably drunk and he was just thinking about stuff, and he had some, let's say cheese. I don't know what it was, but he was thinking about cutting things in half. So yeah, there probably wasn't a bar or enough. There were probably almonds. We'll say it was cheese though because he's fancy. So he's cutting a cheese in half. He cut that half in half, that half in half, that half in half, and eventually he got down to a piece that he couldn't cut. And he thought, basically this is his entire contribution, is he thought, wouldn't it be interesting if there was something that couldn't be cut? And I will call that, it can't be cut, atomos. And then for several years, people were like, that guy's crazy, we're going to listen to Aristotle who says that everything's made of earth, fire, water, and air. And so they did. But eventually, so this is his contribution, is just the word, pretty much just the word, the idea that there might be something that cannot be cut. Later on in the early, this says 1900s, I think it was probably the late 1800s actually, but then the early 1900s, there was this idea, I think your book is missing a model that I would kind of like to talk about, but I cannot for the life of me. Oh, Dalton's model, here we go. Dalton, not Dalton Norman. Dalton's model was next, and this person had actual evidence, John Dalton, and he's in your book, but he had actual evidence that when matter interacts, when matter undergoes chemical reactions, it actually does behave as if it were made of these small particles. So he called that an atom. Even though for more than 1,000 years, for almost 2,000, maybe even more than 2,000 years, people had understood that the world is actually made of earth, water, fire, and air, like those primordial elements, which is not true, but that's what people assumed for a long time. But when he came up with this idea that actually they really do behave like these little particles, he renamed it atomos after Democritus' idea. And his was just that all matter is made of these discrete, meaning individual, particles. So it's just a ball, just a solid ball, and to him, the solid ball is what made matter up. What's up? Yeah, there are loads of them in the bottom drawer in the lab there. So Dalton's model was just, to him, just a solid ball that made up all matter. By the way, and I don't think I headed this, but this is in Greek. We're talking about atomic models here. What's a model? Remind me. We talked about this at the beginning of the year, so you should know, but what's a model? Yeah, not always a demonstration. That's a good way to think. Yeah, thanks, Doug. It's a thanks for that lovely noise too. A model is a way that we can understand a concept, even though we know it's not the entire truth. So the first one, not really a model at all, just kind of a word. This one, his model was just that they are solid balls. And then we have the idea, the next one to come around was in the 1900s. This is called Thomson's model. And this was that there was, in Thomson's model, there was a positively charged matrix. This is sometimes called the plum pudding model. And inside that positively charged matrix were lumps of negative charge. Which, plum pudding in England at this time was basically like really gooey cake that had plums in it. Or I usually say, we would probably call it today like the chocolate chip cookie model, where the cookie itself has a positive charge and the chocolate chips have a negative charge. So his was a solid ball, but with negative charges spread out within it. That's Thomson's model. What do you think was discovered? What real physical thing that was discovered probably led to this model? Charges, yeah, the electrons. He discovered electrons. Or electrons were discovered and he devised this model to explain how the atom could be made of smaller pieces. Because remember, the prevailing model at the time was just a solid ball. But he was able to break up atoms into their subatomic particles, and so that he considered this model. The next one is called Rutherford's model. And this is the one that when you look at the Jimmy Neutron title sequence or whatever, the idea was that he found that atoms are mostly empty space, like we talked about earlier. Atoms are mostly empty space, so he put the nucleus in the middle, surrounded by orbiting electrons that have the orbit-like planets in the solar system. We still use this symbol a lot for atoms, and actually, we still sometimes use this model to show how atoms behave, but it's pretty rare.
Will you say that name again?
Rutherford's model. The next one is called Bohr's model, named after Niels Bohr, and his kept the idea that atoms are mostly empty space, because they are, and he found that electrons actually exist in discrete, that is, individualized energy levels, that electrons have energy levels. That some electrons have more energy than other, and the more energy they have, the further away from the nucleus they get, is Bohr's model. And then the modern model, or the one we use today the most, is called the quantum mechanical, or electron cloud model, where it's the nucleus in the middle, and then there's just kind of this hazy, it's kind of hard to draw hazy with a dry erase marker, but there's this hazy cloud of electron activity around it. What was discovered that made us lean more on this model is that the electrons don't actually move in circular orbits. They do, as I told you yesterday, they snap in and out of existence. One's here, and then it's over here instantly. There's no continuous motion in a circle. And they have these areas where they can exist, which is called the electron cloud. So these are the different ideas of atoms throughout time. Starting with just the name atom from Democritus. I didn't draw a little picture for that because there wasn't one. Dalton's model that it was a solid sphere of that substance. Thomson model, sometimes called the plum pudding model, which was a positive matrix with negative charges spread throughout. Rutherford's model, mostly empty space, true, and electrons around it, true, but not in discrete orbitals. Bohr's model added the discrete orbitals, and now we know those orbitals are not so much circular orbits as they are just areas that an electron can exist in. Yes?
What's inside? Like, there's protons, neutrons, and
Well, protons and neutrons are made of quarks, and electrons are fundamental. Electrons were part of the quantum mechanical model, and this is not something you really were super interested in, maybe, Gunnar or Hunter, but electrons behave much less like solid chunks, like marbles, like I showed you yesterday, and more like they're crests and troughs of a wave. They exist just for a split second, and they stop existing. And they're not really real physical permanent things. Anyway, let's talk a little bit more about the quantum mechanical model which we use today. Specifically, and I also want to talk about Bohr's model a little bit more, but specifically I want to talk about the energy levels that Bohr devised, and I want to relate them to the periodic table. So I'm going to erase this part. Hopefully everyone's done with this, and you can keep working on your drawings and explanations of the models of the atom while I move over here to talk about energy levels. Electron energy levels. What is an atom mostly by volume?
nothing.
Yeah, it's mostly empty space. What is an atom mostly by mass? No. What makes up most of the mass of the atom? The nucleus, the protons and neutrons. Okay? So the protons and neutrons are here. We normally say in the middle. Let's say this is an atom. Pick one. We know we should know how to do these still, but let's no. Let's use aluminum since that was the one some people did for their lab. Let's say it's aluminum 27. We have an atom here of aluminum 27. I'd like you to draw this with me. Aluminum 27. What's the 27 mean? Let's be a little bit more specific. What's this 27 mean?
That is the amount of protons and neutrons in it.
Yes, that's as specific as I wanted you to be. It has a name though. What is this? What's
Isotope.
No, this whole thing is an isotope. Aluminum 27 is an isotope.
Mass number.
It's the mass number. This is the mass number. This is called isotope notation. But we also sometimes write it this way. Let me show you something here real quick, because this will be on the test. What's this? What's this AL mean? Pew! Yeah, you little devil. This is what we call the symbol for aluminum. This is the symbol the chemical symbol for aluminum. This is the chemical symbol for aluminum. And we have 4 little squares that we sometimes use on each corner of it. This is not a normal thing for people to draw, but I just wanted to show it to you. Up in this corner, we have the charge. So sometimes an atom can be charged. Actually, that's not true. If the atom has a charge, we call it an ion. Charge, if an ion. Anytime the atom has a different number of protons and neutrons, remember they're supposed to be the same. How many protons does aluminum have? Look at, how many protons does aluminum have? 13. How many electrons does it have when it is an atom? When it is a normal, just a, how many is it supposed to have? Yeah, 13. They're supposed to cancel each other out. It's supposed to have the same number of protons and electrons. But when it combines with other atoms, it can get a charge. For aluminum, that charge is always 3+, and that's where this is where the charge goes, is in the top right corner, if it has a charge. And if it has a charge, we no longer call it an atom, we call it an ion. That's what the word ion means. An ion is a charged, I'm going to put in quotes, atom. Because it's not an atom anymore, it's an ion. This down here is where we would put the amount, if there is any. So for instance, if this was aluminum oxide, Al2O3, you know about H2O? Yeah. 2 hydrogens and 1 oxygen. This, yeah, the amount goes here. So if it was Al2O3, the amount of them goes there. However many aluminums are in that substance. Are you writing this down? This is pretty important for you to write down. In this corner, oops, I drew my arrow a little bit too far. Oops, now I've erased it really badly. What a mess. In this corner goes the mass number of this isotope. So for this isotope, what is it? Where do I put there? 27. And this corner goes the atomic number. This is not always necessary to write. In fact, it's never necessary to write. Why would it not be necessary to write the atomic number? You always know it. How? Because it's on the periodic table. What is the atomic number of aluminum? 13. And it's always 13. This tells us the same thing as this. So we don't always write this atomic number. But just so you know, and this would not have boxes around it normally. Normally it would look like this. If you just see it, it would look like this. I'm not going to put the amount because it wouldn't really have any. But this would tell you all the information you need to know. This is another way of writing isotopes. We have 2 ways. Whole name hyphen mass number, and this notation where it tells us symbol, mass number, atomic number, and a charge if there is one. And if we're doing the same thing, that charge has to go there in the name. So we have these 2 pieces of information are the same. Okay? Both of them have everything we need to do this. How many protons altogether? 13. How did you know? Because it's aluminum. In this notation, you can look down here, but it's aluminum. You should be able to figure out from the periodic table what's its number of protons. How many neutrons?
14.
You don't have to show this. I saw a lot of people showing this on their bell work. You don't have to show this, but it's equal to the mass number minus the atomic number, which is, as you said, 14. You don't have to show this little, you don't have to show this little, yeah, where's the mass number at? In this one, it is,
where did you get to?
it has to be given to you. You cannot find on the periodic table. Thank you for pointing that out, Taylor. Actually, a lot of people try to look at this number down here as the mass number. That is not it. For these ones, this is always given to you. I made it up, is how I got it. For these ones, it's always given to you. It's always a given. So in this format, you'd see it up in the top left corner. In this format, you see it after the hyphen. It's always mass number minus atomic number, and the mass number is always given to you. Do not use the periodic table to find the mass number. You will get messed up. One way you can tell is that all of these are decimals. So if you're looking at magnesium and you're about to write 24.3501 as your mass number, wrong. These are always whole numbers. Because in this case, we're talking about a specific atom. And an atom cannot have 24.453 or whatever I just said as its mass number, because it can't have 0.3 of a neutron. That does not exist. What this is the weighted average. This is what we call the atomic mass. I know it's confusing. This is mass number, and that is atomic mass. But the atomic mass is an average. Let's just put that over here. It's a vocab word. You should have already known it, but let's put it over here. The atomic mass is it's called a weighted average, but it's an average of all the isotopes. All weighted average means is that the isotopes there are more of get more factored into the average.
What's the definition of isotopes?
This is an isotope. An isotope is some atom that can have a different number of neutrons from the others of the same atom. So hydrogen 2 and hydrogen 3 are isotopes. The atomic mass, which is given on the periodic table. So if we're looking at the periodic table and we see aluminum, oops, sorry, that should be lowercase. If we're looking at the periodic table and we see aluminum and it says 26.9815, 26.9815, this is the atomic mass. It's the average of all of the isotopes. So there's aluminum 27, there's aluminum 26, there's aluminum 25, and we average all those together and we get this number. Don't use that for this. Okay, back to this. So we found the number of neutrons. How many electrons does it have? Now this is where we need to be a little bit careful, because how many should it have? When it's an atom, it has 13. But this does have a charge, baby.
So 16.
Be very careful, because what's the charge of an electron? What's negative? So must this, with a 3 plus charge, have more protons or electrons? It must have more protons. Can we change how many protons it is?
No.
Can I just make this 16? No, because if I make it 16, now it's sulfur. So that doesn't work. So I must change the number of electrons. So if it's 3 plus, I have to do what with the number of electrons? Subtract 3.
So it'd be 10 electrons.
There are 10 electrons. So if you see a positive charge, subtract electrons. Because now, we would have 3 more protons than electrons. We can't change the protons. 3 more protons than electrons means that now we have a 3 plus charge, which was given. So either of these formats will tell us if there's a charge. Let's do one more of those just because I'm a little bit worried that you haven't quite got it yet, and then we're going to move on to the next thing that I promised we would. Because we haven't even talked about this, which is what I actually headed this thing. Let's do, let's call it, there we go. This might be all the information you're given, just this little symbol. So let's do protons, neutrons, and electrons for this baby. Tell me the protons all together. 30. How did you find it? Just tell me where. On the board. What's that guy's name? Periodic table. Neutrons? The 67 minus 30, which is? Whoop! 37. Electrons? Okay, so be careful. 2 plus, so it must have 2 fewer. 28. This is correct for this. Please read these two down at least. Let me rehead this one for you, just so that you have a couple of examples to go off of.
Can I ask a question?
Please do, Hunter.
How do you get the protons number?
How do I get the protons number?
It's the atomic number.
It's the atomic number on the periodic table. So for tungsten, it would be 74.
I thought that was atomic, or the mass.
Nope. The mass number has always got to be given to you. In these problems, you'll always be given the mass number. So on the board, the hyphen, that's the mass number. So it says carbon 12. 12, as you can see, carbon's atomic number is 6, but the mass number is 12 in that given. There's also exists carbon 14. So I could have said carbon 14, and that one would have a different number.
Will we get the periodic table?
You will get the periodic table on your test, and you will always be given the mass number. You never have to look that up.
Keep that up there.
I'm going to leave, no. This one, yeah, that periodic table, yes. I'm not going to leave this up here. Okay. Let's talk real quick about energy levels, because that's what I actually wanted to talk about. I got a little bit carried away, but that's okay. You feel better about this main problem, right? I'm also going to show you the other thing that we will do on the back page of the test. So let's say I have, as I said before, aluminum 27. Aluminum 27. This one we're not going to have a charge. Actually, let's use a different one so you don't get confused. Let's say I have magnesium 25. Magnesium 25. What should go in the middle of my diagram of magnesium 25? I mean, what things? Don't tell me how many yet. What things go in the middle of my diagram of magnesium 25? Protons and neutrons, okay? So I'm going to put protons and neutrons in the middle. So I have here, you can draw individual circles with a plus in them and individual circles with a 0 in them to indicate protons and neutrons. I usually, and for this, I will just write the number of protons and neutrons. How many protons in magnesium 25? No, that's the exact answer I did not want to hear. 12. 12 protons. How do you find that? Periodic table. How many neutrons?
It would have to be 13.
13. 25 minus 12, so 13. How many electrons would this have? Does it have a charge? No. So how many electrons? 12. So here's how we do it. The first energy level can have 2 electrons. First energy level can have 2 electrons. That's all. Just 2. I'm going to give you a formula after this. The second can have 8 electrons. Okay, so how many do I put in the next level? How many am I trying to get to altogether? 12. I'm trying to get to 12. So I have 8, 1, 2, 3, 4, 5, 6, 7, 8 in the next level.
So you're at 10.
I'm at 10. I need a third level, and how many go in the third level?
3.
Nope.
4.
12 minus 10 is
2.
2. 1, 2. The third energy level can have 18 electrons. But here's the real kicker. I wish you'd write this down, all of these. The real kicker is that the highest energy level, oops, sorry, capital E, the highest energy level, capital E, can only ever have 8 electrons at the most. So whatever the highest one is, we call this is a very important word, the valence electrons. This is so important. I wish this had been the first thing I said so I hadn't already lost your attention, but this is the most important thing in this whole lesson. Valence electrons are the highest electrons. So in this case, how many valence electrons does magnesium have? Just the ones in the highest energy level.
So 8.
No, nope, just the high. It can have 8, but how many does magnesium have? 2. 2 valence electrons. The reason I focus so much, and everyone in chemistry focuses so much on valence electrons, is they're the ones that do the bonding. They're the outside ones. And so just like your outside grabbers are the ones that give people a hug, the outside electrons are the ones that bond with other atoms. And bonding with other atoms is the point